uh, make a quick review before we start what we want to do today. If I have time, I will try to cover two topics. One is the derivation of Maxwell's equations from the principle of least action, that's the field equations. Last time we derived sort of the particle motion in electromagnetic field, the Lorentz force law. Now we do the other half. Knowing the currents, we'd like to derive the fields. Similarly, last time we also derived, in a way, the geodesic equation, which is the motion of a particle under the gravitational field. Now we'd like to do the other half, which is for a given distribution of matter, is to find the field equations, which are found by Einstein. Okay, so but before we do that, there are some things that should be more or less clear in your mind. So last time we derived this. At least I gave it as a homework. I don't know whether people did it or not, but it's not difficult. But it's a bit there's some easiness with vector calculus. So dp dt, that's p is the kinetic momentum of the particle as compared to the canonical momentum, which is partial L, partial V. Okay? What do I mean by that? P is mv. Okay? Called the kinetic momentum, and you do. But the canonical momentum last time, is, and this is equal to, if you take the Lagrangian we derived last time, okay, and just apply the definition for, okay, from the Lagrangian that we derived for the particle in electromagnetic field, okay, that's just P, so that's P plus E over C times A. I'm using CGS units, okay. Very easier to work with. Okay. Let me remind you of the Lagrangian. It seems like you forgot it. The Lagrangian, we derived it to be minus mc square root 1 minus d square over c square plus e over c v into a minus e5. This we derived last time. Okay. So if you do this, you just, so now this means that the kinetic momentum is just p minus e over c times a. And now dp dt, so Lagrange equation then becomes what? All the Lagrange equations. Remember? d dt partial L partial V is partial L partial R. Okay? Now, this means that d dt of P plus E over C A is partial L partial R. Okay? Now, partial L partial R, this doesn't contribute. This and this will contribute. Okay? Should I do that? Because this will give you Lorentz force law. This thing will give you Lorentz force law. Okay? Well, let me do it. Now, this we think we write as the gradient of L. Okay? Now, so this is equal to E over C, the gradient of what? Of V into A minus E, the gradient of phi. Okay? And you start here seeing a part of the electric field. Okay, remember? The electric field, we defined it to be B was the curl A. So let's see how this thing transforms into the Lorentz force law. Remember Lorentz force law? It says dp dt is EE plus E over C V cross B. Okay? So, first of all, what is this? Okay? The gradient of a divergence of V dot A, okay, it's a long formula, but for our purpose, when I'm differentiating with respect to R, I'm taking the gradient, I'm taking it at V equal to constant. Okay? So this thing here simplifies, and I get E, so, sorry, so dE dr, now the gradient of L, will be equal to E over C, so it becomes V into gradient of A plus E over C V vector curl of A. It's a vector calculus identity, that's all. For the divergence of scalar of two vectors, scalar product of two vectors, minus E the gradient of phi. Okay? Clear? Now I look here. I have d E over C dA dt. Now what is dA dt? Well, dA dt is partial A partial T plus chain rule. Okay? Chain rule. And partial A, or if you want, well, let me write it down. Okay? You can write it in component form. The total derivative of A can change because of two things. It can change because it is intrinsically changing with time, or it can change because it's changing on the particle trajectory. Okay? So, if I substitute this thing in here, what will happen? Okay? So I'll have dp dt plus E over C partial A partial T plus E over C V into the gradient acting on A, and this is equal to that. Okay? So this term and this term cancel. Okay? So what is left now is dp dt is this. Now what is the curl of A? Is B, right? That's B. I take this term to this side, and combining it with this term, I have the electric field. So this is E plus E over C V cross B. Okay? And if V over C is much less than 1, that becomes M dV dt is EE plus E over C V cross B, which is the Lorentz force we all learn in elementary EM. Okay? Now let me rewrite this in four-dimensional form. In four-dimensional form. And in the process, I will introduce something we call the electromagnetic field tensor. Okay? Now remember the action we started with? We had the action for the particle, and the action for the interaction of the electromagnetic field with the particle, the charged particle. Okay, and we describe the electromagnetic field using the 4-vector potential, A. Okay, so my principle of least action now says that the variation in the action is delta, the integral, okay, minus mc ds, and ds is just the space-time interval, okay. It's like the proper time, c d tau, essentially, okay. That's the scalar, minus e over c ai dxi, where I runs from 0, 1, 2, 3. Okay? And that has to be 0. What we did there is we said dxi ai is minus E5 plus EV dot A times dt. That's all. I'm not going to do that. Okay? Just leaving it like this and work with it. So remember that ds was the square root of dxi dxi. Okay? And therefore, my action change now becomes delta, okay, with a minus sign. No, I take the delta inside. So this is minus mc, okay. Now I'll have dxi d delta xi, okay, square root, when I derive, it goes to the denominator. So I'll have here ds. Because I'm deriving it twice, the 1/2 also cancels out. Okay, plus E over C, okay, AI delta xi, should say D delta xi, just taking this delta inside, plus E over C delta I dxi. And this has to be 0. Okay, everybody on board? Huh? Everybody on board? More or less? Okay? Fine. I don't think I will skip the details, okay? The algebra. And just write, okay, let me define first. We define UI, the 4-velocity vector, okay, is dxi ds. It's a 4-velocity vector, okay? It has components 1 and v, or v over c, v over c, yes, v over c. Okay, so 4-velocity vector. Hey, with this, now there are some algebraic steps here which I'm skipping. So this now becomes the integral. Excuse me. Let me write it. Top of this. So the integral mc dui ds, and you see this is ui, okay, and then I integrate by part, etc., etc. All of this and minus e over c partial ak partial xi minus partial ai partial xk, xk, the whole thing delta xi ds, and that has to be 0. Okay, just some algebraic manipulation, integrating by parts, exchanging indices, etc., etc., etc. Okay. Now, since this has to be 0 for any variation delta xi, okay, and here I'm of course ignoring when I do an integration by part, the total differential, when I'm integrating it, I'm saying it's 0 at the beginning and the end, because delta xi is 0 at the beginning and 0 at the end. Okay. So this thing here, we give it a name. Okay. This we call the electromagnetic field tensor, FIK. Okay. And therefore, my equations of motion for the particle, okay, since just this equation plus the time component of this equation, which is just the energy rate. Okay, so it tells me that MC, excuse me, dUI ds is equal to E over C FIK UK. And this is the equation of motion of a charged particle in an electromagnetic field described by the electromagnetic field tensor FIK. The special components of this are nothing more than Lorentz force law. The time component is the energy. It tells the energy change of the particle is equal to the work done by the field. That's all. Okay? I did this to introduce the electromagnetic field tensor because we need it when we want to write the action for the field. Okay? The action for the field. Now, what is this electromagnetic field tensor? Remember, before vector potential, we defined it to be just this guy. Okay? And if I go into the covariant component, in my metric, this is just this guy. Now, in flat space-time, covariant, contravariant, it's not very different, except for the change of sign. But when you go to general relativity, they're completely different beasts. Really, they're completely different. Okay. So FIK, if I use this definition, FIK downstairs is just 0. First of all, it's a completely anti-symmetric tensor. It has only 6 independent components, which are the 3 components of E and the 3 components of B. Okay, so let's write them down. So 0, EX, EY, EZ, okay, and then here minus EX, 0, minus BZ, and here is BY. Here it is minus EY, BZ, 0, and here it is minus BX. Okay, and here it is minus EZ, and then minus BY, BX, and 0. Just sometimes just write it as EB. And if I want to find FIK upstairs, okay, in my metric, whenever I change a time component, the 0 component, nothing happens. But if I change the spatial component, X, Y, or Z, I get the minus sign. Okay? So since here I've had 2 spatial components, they don't change. Here I have 1 space, 1 time, it will change. Here I have 1 time, 1 space, it will change. Okay? So this is just minus E and B. And it's the same thing now with just these minus signs switched here, that's all. Okay? So that's my electromagnetic field tensor. It has another name in geometry, it's called the curvature tensor. The curvature tensor. Okay? Yes. Sorry? It doesn't tell us more than what this equation tells me. Just Lorentz force law, but written in the 4-vector notation. And by doing that, I had to introduce the field tensor because I need it later on to write the action for the field. Okay? But this has the special component is just this, nothing more. Okay? The time component, it tells me how is the energy of the particle changing? Well, it tells me that the rate at which the energy is increasing is equal to the work done by the field, which is just E dot V, or Q E over E the charge times E the vector times V. Okay, that's all. Okay, any more questions? Good. Now, notice here that E and B, they are completely, equal in a way. They are the component of the same tensor. They're the components of the same tensor. Because they enter into the equation equally. Okay? Now, what would be if I want to construct invariance, which I would need to write the action for the field, what would be the invariance that I can write for the electromagnetic field? Huh? Where? No, in SI units you have, but here we don't have. That's the beauty of CGS units. E and B is the same. And they should be like this. They are the same, really. Okay. And that still comes from units. Okay. Okay? So what will be the invariance that I can construct? So I have to contract over that would be an invariant. The trace, right? But what is this? It's zero. So it's not very interesting. Another one. Well, this one's square, but still zero. So I can have this one. That's an invariant, definitely. It's a Lorentz invariant. Okay? And if I write it in component form, this is proportional. I don't know, it's plus 2 or minus, so I'm not sure. E square minus B square. So this is like kinetic energy minus potential energy. Okay? Alright? Now, this is a true scalar. What do I mean by that? E is a polar vector. So polar vector. You know what a polar vector is? It's like position vector, momentum vector. It's a vector that changes sign when you mirror image it into a mirror. You take a vector, you look into a mirror, it changes sign, right? That's a polar vector. How about B? It's an axial vector. What do we mean by axial vector? You take a B like this, you point it into a mirror, it's still pointing the same direction. It doesn't switch. Why? Look how it is defined. The curl of A. A is a polar vector, so it's a real vector. But the curl of A is an axial vector. It's like a vector product. The vector product doesn't change sign when you mirror image it. It doesn't change sign. Like the angular momentum or the spin. Now, the scalar product or the square of a polar vector is a true scalar. The square of an axial vector, what do you think? Is also a true scalar. Now, what do you mean by true scalar and not true scalar? A scalar does not change sign when I look a mirror image it, right? It's a scalar. A pseudo-scalar, it does change sign. Take a scalar quantity or a pseudo-scalar quantity, you look into a mirror and it changes sign. That's we call a pseudo-scalar. Yes. Yeah, E is a polar vector, right? So E changes sign when it changes R into minus R. Okay, so E squared doesn't change. Same for B. B does change, B does not change sign when I change R into minus R. So neither does B squared. Okay? So both of them are true scalars. So this invariant is a true scalar. It's invariant under inversion, coordinate inversion. It's an invariant. There is another invariant, but I would not consider it for the action because it's not a true scalar. It's a pseudo scalar. Okay? Well, instead of going to the details, let me just write for you. Okay? It's this one. Okay. Are you familiar with the Levi-Civita epsilon ijk? Okay? This one, you are familiar with it? It's 0 or 1 or minus 1, depending whether you are familiar with that, right? Now I introduce now four-dimensional one. Okay? Four-dimensional one. I call it, what do I call it? IKLM. Okay, IKLM. Yeah, now I and K, these indices run from 0 to 4. Okay? So when you have 0, 1, 2, 3, it's 1. Any even permutation is still 1. Odd permutation is minus 1. Any two indices equal, it's 0. Okay? Now if I contract this with Fik, FLM, this is also an invariant. Okay? And it is E dot B. Now E is a polar vector. B is an axial vector. How about the scalar product? So pseudoscalar, yeah. Pseudoscalar. So even though it's an invariant, I will not consider it for the action. Why? Because it's not invariant under coordinate transformation, under coordinate inversion. My action has to be invariant under anything you do. Inversion, rotation, Lorentz boost, gauge transformation. It had to be invariant. It's a number. Okay? So, that's my candidate for the action. That's my candidate for the action of the field. Not this one. Okay? Now remember, my action, the total action, was the action for the field plus the action for the matter plus the action for the matter field interaction. Okay? Now, the matter Sm, we already wrote it for one particle. So if you have many, just the sum of these guys, the action is additive. So minus sum over MC, the integral ds for each one, for all of them. Okay? And S and F, okay, just generalization of what we had before, sum over E over C, the integral AK dxk. So this is for one particle, this is for all the particles. What is SF? Well, as I said, that's the only guy I have. Okay? So SF, okay? Now in my system of units, okay? In my system of units, I write it as minus 1 over 16 pi c, okay, the integral. Now, because it's a field, my action now will be the integral over an action density, okay, over an action density. And I would like to write it as a 4-volume integral, volume and space, so that the d for x, if you want to call it, which is dx, dy, dz, dt, that's an invariant in the Lorentz transformation. We know that, okay? So what remains is also a Lorentz scalar, okay? So this is equal to f ik d omega, where d omega is C dt dx dy dz. And this is a Lorentz invariant. So this is a Lorentz, we know this is a Lorentz invariant, right? So the whole thing is a Lorentz invariant. Okay? Now I would like to write this not in terms of dxk and E, but in terms of rho and V, but ultimately as a function of J and d3x. Okay? Let's do that. Oh yeah, yes. This is an invariant. This is what we call a measure, integral. So integral measure. The measure has to be invariant. So that when this is an invariant, khalas, you are finished. You don't have to reinvent. If this is not an invariant, this will change. This cannot be an invariant. If this is not an invariant, this is a scalar. That cannot be an invariant. Then you have a problem. Okay. Any questions? Muad? Okay. Right. What I would like to do now is define a 4-vector current density. Okay. So we define it. If you want here, we define the charge density in a way sum over the number of particles, EA delta R minus RA. The sum here is over A, number of particles, okay, or N. Excuse me. Now I define the 4-vector current J sub I. Okay, this is equal to rho dxi dt. Okay, yani in a way it is C rho, that's the term component of the vector, and J, that's the vector component of the vector, where J is the rho v. Okay? Now I assume like the particles now are dense enough so that I can define a function, we call it the charge density, rho. Okay? Now the integral, now I'd like now to rewrite this as a function of J. Okay? So let's rewrite that. So minus 1 over C, this term here, the integral of rho a sub I dxi d volume, okay, rho, integral of rho dv, that's the sum over E, okay. So this is equal to minus 1 over C squared, the integral over AI. Now I introduce rho dxi just ji dt, okay, ji dv dt c dt, because I'm dividing by C squared here. Okay. Yes. Yeah. This integral is really four integrals. 1 over time, 1 over x, 1 over, well, let's say 2. 1 over time, 1 over the volume. No, not necessarily. Not necessarily. Not necessarily. Not necessarily. You see, yeah, this is my definition. Not necessarily. Okay? Now this is my d omega, my 4 volume. Okay? Okay. So now my action now becomes S is what? Minus the sum MC, the integral ds over all the particles, minus 1 over C squared, the integral. Now there is no more sum term here because I integrated, etc. Make it into a current. AI, JI, d omega. That's the matter field interaction term. Okay? And then I have 16 pi c, the field term, Fik, Fik, t omega. That's my action. Okay? So the first one is just the particle matter action, matter field interaction, field action. Okay? Now before, I wasn't considering this because I assumed that this is a fixed background. Okay? AI is fixed. So I vary the coordinates of the particle, okay? By minimizing, I find the equation of motion of the particle in this fixed background of electromagnetic field. Now I want to do the other way around. I want to assume that the particles, they have a fixed configuration. What I mean fixed? They are moving, okay. But they are moving along those trajectories for which all Lagrange equations are satisfied already. The physical trajectories, okay? I'm not trying to find an equation of motion for them. I know what it is, okay? So now what I want to do is for a fixed distribution of charge, fixed not any fixed terms doesn't change in time. Fixed means known. For a known distribution of currents and charges, okay? I would like to find the equations of motion for the field. So when I do the variation now, I don't consider this term. Because this term now for me is known, khalas. This is not known. The equations of motion for the field is not known to me. When the field now is interacting with distribution of currents and charges, what are the equations that will tell me what the field is? The dynamical equations of the field, what are they? Okay, before I wasn't considering this. That gives me the Lorentz force law. Now I ignore this, consider this too. What do I get? Maxwell's equations. Okay? Let's do it. Any questions? Huh? The whole thing? You cannot solve it. You cannot solve it. What will you get? You cannot solve it. Huh? Yeah, you can, what will you get? Try. See how it works. طيب. So, in CGS units, what am I? Yeah, okay. Finished with this. Okay. First of all, the first pair of Maxwell's equations. What do I mean by the first pair of Maxwell's equations? There are, huh? Yeah, essentially, yes, you're right. You see, B equals the curl of A. And E, right, this is the, from here, the divergence of B is always zero. Okay? So if you give me a magnetic field whose divergence is not zero, I tell you this is nonsense. So these are like boundary conditions, if you want. I don't know what to call them, but these are like identities which the field that you find from the sources have to satisfy. I give you any distribution of charge and currents. You find A and B. If divergence of B is not zero, that's the wrong answer. I know. You see what I mean? Okay. So these are not really laws in a way. They are limits on the laws. The fields that you find have to satisfy these things. These are what you call identities. Okay? So divergence of B is zero. Has to be, right? Because it's the curl of A. And this, take the curl of E here, what do I get? Yes? 1 over C, and exchange the curl of partial time derivative. So I have partial T, the curl of A, minus the curl of the gradient of phi. Now what's the curl of a gradient? It's always 0, okay? What is curl of A? That's B. That's what you know as Faraday's law, okay? This is nothing more than Faraday's law. Okay? So Faraday's law is not really a law. It's an identity. Okay? So the curl of E plus 1 over C partial B partial T is equal to 0. Any field you find, E and B, has to satisfy these two identities. Otherwise, they are the wrong fields. Okay? I can rewrite them, these two sets of equations, in one. 4-dimensional equations. Okay? Well, I'll just write it for you using the electromagnetic field tensor. So I say partial F IK partial XL plus, and then I do rotation. Partial F KL partial XI partial F Li partial XK. This has to be 0. So this equation and this equation are nothing more than this. Okay? This has a name. What do we call it? In differential geometry or whatever, I don't know. Called Bianchi identity. The Bianchi identity. And I'm not sure how to I think this is how it is spelled, but I'm not sure. Identity. You see, it's identity. So it's a constraint. It's a constraint on the fields that you find. It's a constraint. They have to satisfy this identity. Isn't it interesting? Faraday's law, which is the basis for the world economy in a way, right? It's an identity. I don't know, it's a topological property of the electromagnetic field in space-time or something like that. It's very interesting. Really. Maybe something deep behind it, I'm not sure. And you would be interested in finding out what this becomes if you have magnetic monopoles. Okay? Does it still remain or have something else? Okay. Any questions? Huh? Yes. Yeah. Even this one will change. Even this one will change. This will not be 0 and this will not be 0. It will not be 0. This here will be rho magnetic. Just we have rho electric. And this will be J magnetic. Like we have J electric for, what's his name? Ampere's law. Okay? But so far, we don't have any magnetic monopoles. So I guess we can use this equation. Okay, so let's go to the field. Again, I don't want to, because we still have to talk about relativity a little. So now what I do, I just vary this part of the action. Clear? So I'll do delta S is equal to minus 1 over C Ji So you see, I'm not varying J. J is fixed. But I'm varying now the potential, the fields, delta AI, plus 1 over 8 pi. Okay, because this, when I vary this, I get a factor of 2. It's like a square of something. Okay, F I K delta F I K, and then I have d omega. This has to be 0. Okay, now I'll save you the pain of the algebra in between. Okay, but this is where you start. And what you end up with is this. So this is equal to 1 over C Ji plus 1 over 4 pi partial F I K partial xk delta AI. You see, these are now my variables, which they are 0 at between two configurations. The initial configuration, they are fixed, so delta AI is 0 there. And the final configuration of the field, they are also 0. They're fixed there. But in between, they vary. But it's a virtual change. It's not a real change. It's a virtual. It's like calculus of variations, right? The delta, this delta is a virtual change. It's not a real change, like in time. The D, that's a real change. Okay? This delta that you see is a virtual change. You think that by minimizing this, making them change with fixed initial and final configurations, and by changing them here and saying that the action is changing, the action is 0 for this change, okay? You get something like this, because these are now arbitrary changes in between. This has to be 0. This has to be 0. And therefore, my equations for the field are F I K partial xk is equal to minus 4 pi over C Ji. And if you do the time and space components of this, you will find that the divergence of E is 4 pi rho in CGS units. Excuse me. And the curl of B is equal to 4 pi over C J plus 1 over C dE dt. Please go ahead and do it. When you go home, just take I equals 0 and K equal, cannot be 0 because it becomes F00 is 0. K equal 1, 2, or 3. Okay? You get one set of equations. And when I is 1, you get the x component of it. When I is 0, you get this. When I is 1, you get the x component of that. When I is 2, you get the y component of that. When I is 3, you get the z component of that. So these are your Maxwell's equations. I'm sure Maxwell will be happy. He will have a big smile on his face. Let me make a note here. That equation now, if I derive it once more, okay, Fik, now I have dxk, now I derive with respect to dxi. Okay, what do I get? Huh? Minus 4 pi over c, yes, dji dxi, right? What is this? Remember Fik is an anti-symmetric tensor. And xk, this is a symmetric operation. So obviously this is 0. Okay? Because this is here, symmetric under the exchange I and k. This is anti-symmetric. So when I contract the anti-symmetric tensor with a symmetric tensor, I get 0. Okay? This is zero. This tells me that partial J, you know what this is? Continuity equation. Okay, it just tells me that partial rho partial T plus divergence of J is zero. What is this? What does it tell me? The charge is conserved. Charge is conserved. So the antisymmetry of F, in a way, is essential for the conservation of charge. And the antisymmetry of F, as I told you, F has another name. It's called the curvature tensor. What it's telling you is that you derive this way, you derive that way, okay? Is the same as you derive this way and you derive that way. Okay? Partial xi, partial xk. Remember? Partial ai, partial xk, minus partial xk, partial akxi is the same as partial xk, partial ii, minus partial xi, partial x. Why is it so? Maybe because charge is conserved. Okay? And it is actually, it is. It is. If you are interested, I can give you another derivation of this, another point of view on this, geometrical point of view, using the language of group theory. Okay, very illuminating, very illuminating. Finish now with the whole of electrodynamics. Lorentz force law, Maxwell's equations, Bianchi identity as a bonus. Okay, and that's it from delta S equals 0. Okay, now we go to another field in nature that is of importance to us, and that's the gravitational field. Now, for the gravitational field, there are certain things you have, some of you might know, some of you might not know, but there is a lot of luggage in terms of terminology and math in order to understand what the symbols mean. So I will not go into the deep, because that takes a whole course. Okay, like parallel transport, covariant derivative, Riemann tensor, Riemann tensor, curvature tensor. Okay, all of that, needs some time to really to introduce. So I don't have. If you're interested, you can. But some of you are taking general relativity in math department. I understand. So probably have seen that already. But if others are interested, we can talk about this later. Okay. But for now, this is not my interest. My interest now is really to again derive the Einstein field equations from a principle of least action. That's all. So assume, wrongly or rightly so, that you're already familiar with some of the stuff. The first thing that you have to realize when you go into curved spacetime is that the four volume, the omega we defined before, is no more an invariant. It's not. Okay? Because the metric is changing now. Before the metric was flat. Okay? Now it's changing. So we have to find another invariant for volume. You know what it is? Yeah, square root of G. Or in our metric, minus G. Okay? Where G is the determinant. You know that if you go from X to X prime, how does the 4X change? Okay? Jacobian, huh? Yeah. Which is just the determinant of this matrix. Okay, this is how it changes. This is Jacobian. Determinant of this, and the determinant of this is, the determinant, this is, we use a lot. I will not use it here, but we use it a lot. The determinant of a matrix, we have to write it in a very funny way in order to be able to derive what we want to do. Okay, I assume it's known, but the determinant of the matrix is the exponential of the trace of the log of m. I don't know if it's imperial log or it doesn't matter. Okay, I don't know how to derive this, but we use it a lot because we'd like to do that. Huh? Any matrix. Any matrix. Yeah. Determinant of m is the exponential of the trace of the log of m. Okay? Yeah, the log, you have to do the Taylor expansion. That's what it means. Yeah. Yeah, the log of anything f of m, where m is a matrix, you have to expand that f in Taylor series, then it's a power. Okay? Okay, Shabam? So I assume this is no. So I'll just tell you that the invariant volume now is no more d for x. It's not the omega, that it's square root minus, or if you want, the absolute value of g. Okay? In our case, because we took the metric signature of the metric is plus for time and minus for space, so you get the minus sign. Okay, that's why we have a minus sign usually here. But if you take the positive for the space part and negative for the time part, you just get g. Okay, so we just write it as absolute value of g. Okay, or if you want d for x, that's equal to, okay, that's my invariant volume. That's my invariant volume. We need this. Okay, I will not derive it. Just take it on faith. Now, my action, it has a name actually. It was Hilbert who first introduced it in 1915. As early as 1915, Hilbert introduced the action and derived Einstein field equations. Okay? Relativity. But he gave, he didn't want to argue with Einstein. Said, oh, you found it first, so we call it the Einstein-Hilbert action. Okay? Einstein-Hilbert action. So you call it EH, I guess. Okay? A constant, which when you go to the non-relativistic Newtonian mechanics, blah, 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 it comes to be 1 over 16 pi g. Where g here is Newton's constant. Newton's gravitational constant, 6.67 times 10 to the power minus 11. Okay? And why it is so small? It's the whole theory behind. The integral, square root minus g, d omega, and I want a scalar here, right? Because this is a scalar. When I mean scalar, invariant. I want something here that is also a scalar. In general relativity, I don't have any scalars. It's tensors all over. There's only one scalar that I can work with. At least the simplest one. Which one? Have you reached this far in your course? Yeah, when probably you know Christoffel symbols, right? Ricci tensor, Riemann tensor. How about Ricci scalar? You take a Ricci tensor and contract it. Take the trace. This is the guy. That's the only scale. We call it R. Okay? I don't have many choices. At least the simplest choice, that's the one. What R now, okay, is what you call the Ricci. You see, in Italian, Bianchi is CH. CC, that's Ricci. Why, I don't know. Ricci scalar. What is it? Just the trace of the Ricci scale, Ricci tensor, which I can write as G nu nu R nu nu. Well, this now is the Ricci tensor. Any questions? Now, what is the Ricci tensor? Well, it is related to the Riemann tensor, which has 4 indices. Okay? But I will spare you that. I'll just write it symbolically. So when you say R, okay, symbolically, is partial gamma partial x minus partial gamma partial x minus commutator gamma gamma. And then you put indices here. These guys have 3 indices. So you have to contract with 1. Okay, similarly here. But the indices, they go as needed. So here you have 3 and 3. So this guy and this guy have to be contracted on 1 index. So you have 2 and 2 left. Okay? So that's the definition. Yani Ricci tensor is related to the Christopher symbol. Christopher symbols are not tensors. They are not tensors. You know why? Yes. You know why? They don't transform like tensors. Good. Yes. Good. Yes. It's true. Huh? No. Yes. That's true. Yes. I can find a local frame in which gamma is 0. If it were a tensor, it will be 0 everywhere. I have no curvature. But I know this is not the case. So it cannot be a tensor. It cannot be a tensor. Okay. But what you said is correct. Okay? So that's all you need to know, really. Now, so when I do my variational stuff, and they say this is 0, okay? So I have to take my delta inside. So my delta will act on this and that. Okay? Remember, my variables for the field here are G mu nu. G mu nu, like the vector potential for the electromagnetic field, is A. That's the field variable, dynamical variable of the field. Here it is G mu nu. That's the dynamical variable for my gravitational field. Okay? These are the Q for the particle, if you want. Fine. Or like this as partial gamma minus partial gamma. Now let me take just a little break. Look at this. What do we call this? A curvature tensor. Huh? It is the difference between two differentiation and, or is it a plus or a minus? Doesn't matter really, but a plus, okay. Plus the commutator. If my gamma had 1 index only, like the vector potential. If my gamma was a vector potential, was a vector, here it is, it's not a tensor, but something that has 3 indices. But assume it has 1 index, and it's a vector, 4 vector. What would that be? No? I could have R, I, J, I, J, minus J, I. But here if it's a vector, A, I, A, J, that's 0. Because the vector potential is like a mute. They're not matrices. صح ولا لا؟ So if I put here AI, AJ minus AJ, partial J, partial I, what is this? What is partial I AJ minus partial J AI? What is that? Fij. That's the field, electromagnetic field tensor. And that's exactly what it is. This is a generalization of that. For the electromagnetism, we have what you call in group theory an abelian group. Because A is just a number, a function. It's not a matrix, abelian. The only thing that changes there is the phase. So this guy is zero for electromagnetism. But for non-abelian gauge theories, like Yang-Mills, aha. Now my fields are not just functions, they are matrices. And matrices do not commute. So if I put non-abelian now, this is non-zero. And gravitation, just an example of that. It's not the only one, just one example. Just one example. Okay? So if you're interested, we can talk about this another time. But for our time, for time being, now, in math, the A's and the gammas, they're called connection one forms. I don't know who took differential geometry here. They're called connection one forms. Connection one forms. They allow you to connect a point in space-time here to another point here. They allow you to find what you call the covariant derivative. How to displace a vector parallel to itself. Connection one form. They connect 2 points in that space in a way that allows you to know what's happening to that vector. Okay. So much for that. So when I say this is zero, I have to find delta square root of JR. Okay. This is what I have to calculate. Now what is that? There are few things here. So I have to write this as delta square root of G R G mu nu R mu nu. Because eventually I would like to express, like I did before, something delta G mu nu integral the omega minus G equal to 0. And this is true for any delta G mu nu, and therefore this has to be 0. Eventually this is what I'm trying to get at. Fine. Here I have 3 terms. One from here, one from here, one from here. Okay, so let's just do one at a time. So delta, excuse me. So this is equal to root G R mu nu. Let me write it mu nu here. Yeah, mu nu. Okay. So R, I'll have R mu nu delta G mu nu. And that's straightforward. That already has delta G mu into it. I don't have to do anything to it. Okay? So that thing here, this thing goes into here already. Okay? Or I should say this one, because this one stays outside. So this already, I will have a term here, I mu nu. Okay? Let me tell you, Einstein, when he first found his equation, he had this term. But the second term, he could only get it if you apply the Bianchi identity. If you don't apply the Bianchi identity, you get the wrong equation. That's why the Bianchi identity is a constraint on the equations. It's a constraint on your field or whatever. You get my point? There's another term here, which if you don't use Bianchi identity, you don't get it. By imposing the Bianchi identity, it has to have this term. Okay? Fine. Plus R, okay, delta square root of G, Okay. Now R just R mu nu G mu nu. I don't write it as, doesn't matter how you write it, but just leave it as R because this the delta now is here. Because when I do the delta, I have to separate these two. Plus root G mu nu delta R mu nu. Three terms. Okay, the first term is trivial in a way, and it goes here. The second term, we'll see in a moment what it is. But the third term, you have to take it on faith. It takes a long and complicated way to show it. But this term is just a total divergence. It's a total divergence. So when I integrate over the volume, I use Gauss's theorem. What this gives me? A surface term at the boundaries. And at the boundaries, the fields are, there's no variation at the boundaries if you want. Or you say the fields are zero at infinity, so it drops out. Even though it's not zero by itself, but it gives zero contribution to the variation of the action. Okay? And to show this, we have to use another identity. Okay? I don't even remember. I don't remember what the name is. I'll find out. It's another Italian name, Italian sounding name. Okay. So this is now, we can ignore. Because it gives me a surface term which is zero at infinity. No need. Now what is this? To do this, we have to use this. So it's the square root of the determinant. So it's the square root of that. Which is 1/2 of this. Whatever, I don't know. Something like that. Okay? So let's just write it for you. So delta root of G, this is equal to 1/2 root G, okay, G mu nu delta G mu nu. Okay? You can show, it's not difficult, but it takes some calculations, some ease with tensors to do, but it's not difficult. Now I have delta G mu nu upstairs. Okay? I want to bring it downstairs. Then I bring this one upstairs. Because my fields are the G mu nu downstairs. Not actually, this is downstairs. Okay? You know why? Because when I write the metric, I write it like this. These are two contravariant vectors, right? And the metric is down, written with the indices downstairs. This is my field. This is my field. And this, as I told you in gravity, G mu nu is a different beast than contravariant and covariant, they are different. Okay, it's like the inverse of the other somehow. Okay, so how do we write delta G mu nu? This guy. How do we write it? Well, we write it like this. This is minus. Now, how do we derive this? It's easy. G minus 1 is 1. Where G is G mu nu and G minus. So this is like G mu nu. G nu sigma. Okay? This is delta mu sigma. Where delta mu sigma is the canonical delta symbol in 40. So this is, if you derive this identity, then you get this minus sign. Okay? And this minus sign is crucial. Because that's the minus sign that goes here. It goes here. So this is minus G mu sigma, G nu lambda, delta G sigma lambda. Okay? I'm almost finished. So all you have to do now, okay, this thing here, write it here, and this sigma and um, sigma and nu, they will contract this r mu nu. Okay, so this will go up. And I change the names again and call them mu nu again. Mu nu upstairs for R, mu nu downstairs for G downstairs. Okay? Alright? So what do I get then? So I have this term, R mu nu, what is it? Yeah. Okay, let's write it down. So what do I get? Delta. So delta S, Einstein-Hilbert, is minus 1 over 16 pi G integral d omega square root of G. And then I will have minus R mu nu. That's the minus sign I get from here. And I get plus 1/2 of R from here. Okay, and this. Okay, G mu nu times delta G mu nu. And this has to be equal to 0. Okay? And this must be true for any variation of delta G mu nu. Any variation. Okay? So this means that this has to be 0. But now my equation now becomes, just like we did before, R mu nu minus 1/2 R G mu nu is 0. And these are the Einstein field equation when there is no matter. There is no matter. I'll be finished in 5 minutes. So what happens if I have an interaction? If there is a matter, if there is matter around or energy, how does this change? Okay, remember how the electromagnetic field interacted with the with the electric current? This works, huh? Now this becomes G mu nu. That's the field variable. And it has to be a scalar. So I have to have something in here that has two indices and describes matter. What is that? What do you think that is? What describes matter and it has two indices? And it has energy in it. Energy momentum tensor. Okay? Energy momentum tensor. We call it T mu nu. Oops. T mu. Okay? It's an appropriate constant. Appropriate constant. So this is just a generalization of that. Okay? When you do that, okay, then okay, so delta S for the interaction, the field matter interaction, will be 1/2 the integral delta G mu nu d and then square root of G d omega. Okay, something like that. Alright? Therefore my equation now will have what? I'm really going here, condensing many things. So it will have this term T mu nu instead of 0. So I have R mu nu minus 1/2 R G mu nu is equal to minus 8 pi G T mu nu. And these are your famous Einstein field equation for the gravitational field. Okay? Give me 1 minute. Notice? This is interesting. Now, when you wrote the Einstein field equation, you said it is this. And then I have R, right? With right? But there is another term that is allowed. There is another term allowed. And it's also a scalar. That's this one. Without the R. This is also an invariant. And it depends on the metric. It depends on the metric. The metric is here. But it's an invariant. So when I vary, this will contribute. Lambda 0. That's what we call the cosmological constant. Cosmological constant. So the cosmological constant term is allowed by general covariance. Okay? What the number is very small. It's not zero, but this is what is thought to be behind the expansion of the universe. Is it related to dark energy? Could be. Okay, but it's allowed. It's there. You can actually include it if you want. Okay, Shabab. So we derived the geodesic equation last time. This time we derive the Einstein field equations, albeit in a rather truncated way. Huh? Because it gets technically involved there, really, if you want to go into the details. But it is there. So that's all of physics. Okay. If you're interested, then we can talk about what I said before, the group theory language of this. Okay, it has a different flavor to it. It has a different flavor. It's also it's good to know. Okay, thank you very much. Any questions? Well, okay. Yeah, Einstein added it before because you see when you're the equations here, you can always he added it. He said plus lambda or here lambda 0 g mu nu. Okay, he added it and then he removed it. And he said, I made the biggest blunder in my life. Because it's allowed. It's allowed, okay? And it was later realized, because at that time, the prevailing view was we had like a static model of the universe. There was no expansion. Okay, but if you have this term here, this allows for expansion. This allows for expansion of the universe. Okay? So at that time, they didn't want it. But it's there. It is there. It's allowed by the equations of, it's allowed by the action, just like it's allowed by the equations of motion. Okay. Yeah. All right.